Hello everyone, welcome back to Abstract Algebra. Today we're going to be talking about finite abelian groups, and in particular we're going to finish the proof of the fundamental theorem of finite abelian groups, which gives us a classification of finite abelian groups up to isomorphism. It says that a finite abelian group is the direct product of cyclic groups of prime power order. What we have done so far is that we have proved that if G is a finite abelian group, then G is isomorphic to the internal direct product of its P primary components. So what remains to show is that each P primary component is the internal direct product of cyclic groups of prime power order, where the prime is fixed now. So let's do that. For that, I'm going to first need a lemma. I'm going to need the following lemma. Let G be a finite abelian P group for a prime P, for a fixed prime P. Remember that means that G is of order a power of P, or equivalently, we proved that it means that every element has a P power order. And suppose that G in G is of maximal order in G. Then there is a subgroup H of G such that G is isomorphic to the group generated by G cross H. Why does that help? Because if, say, the maximal order is P to the M, then this group generated by G is isomorphic to Z modulo P to the M, and then we're going to be able to use induction on H now and decompose H as a product like this, and then get to show that every such group, every group that is a P group, an abelian, finite abelian P group, satisfies the conclusion of the big theorem. Okay, so let's give a proof of this statement. So here is the proof of the lemma. So we have seen that G is a finite P group that is abelian. That implies that G is of order a power of P. And we're going to use induction on N to prove our statement. So if N is equal to 1, then the size of G is P, and that implies that we have seen that a group of prime order is cyclic, so G is isomorphic to Z modulo P. Z, which is isomorphic to Z modulo P cross the subgroup that is the identity, so that's my H, and therefore the case of N equals 1 is proved. So now let's assume for our induction hypothesis that the statement is true up to N minus 1, and let G be of order P to the N as in the statement, and take G in G of maximal order. The order of G has to divide the order of the group, so let's say that G is some P to the M. That implies that the G to the P to the M is the identity, but in fact, it also implies that every element in the group to the P to the Mth power is E for all A in G, because every element has to have a prime, a p power order, and if p to the m is the largest one of all, then any element to the p to the m has to be the identity. Great. So now I want to construct this other subgroup H, and how I'm going to find H is as follows. So let H be in G such that H is not in the subgroup generated by G, and H is of the smallest possible order, smallest positive order bigger than 1, so not the identity, with this condition. Notice that if no such H exists, every element that is not in the subgroup generated by G is identity, then that would mean that then G is isomorphic to the subgroup generated by G, which is isomorphic to the subgroup generated by G times the identity. And again, if I call that H, we would be done. Right, so we can assume that there is such an H, and I'm going to let, for now, K be the subgroup generated by H. Okay, that is not going to be my H, but so I'm gonna call it K, and by what I just said, the subgroup generated by G and K has to be of trivial intersection. There's nothing in there, otherwise I would be able to generate H as a power of G, but H is not in the subgroup generated by G. Okay, so what does this get me? We have some element in G that has the largest order in G, and I have an element H also in G that is not in the subgroup generated by G. In particular, H is not the identity. And with the smallest possible order, I'm going to let K be the subgroup generated by H. So note, first of all, that the order of H must be P, because I know that the order of H is some power of P, and that implies that the subgroup generated by H has an element of order P. Let me fix this a little bit. It has an element of order P, and H was of the smallest possible order in the rest of the big G, so that means that the order has to be P. Or if it wasn't just some appropriate power of H, it's going to give me an element of order P. So H has order P, and what we're going to do then is now consider this other group. I'm going to use the induction hypothesis on this other group, because now this other group has, this is another abelian group, but the order is the order of G, which was P to the n, divided by P. So this is of order P to the n minus 1. So the induction hypothesis is going to apply here. So I just need to find an element of the maximal order in here. What is the induction hypothesis? This is the statement that if I find an element of the maximal order in the group, then this element breaks off with a complement in an internal direct product. So what I need is to find an element of maximal order in here, in this quotient, and I'm going to claim that in fact the order of GK in G modulo K is the same as the order of G, which was P to the m, which was the maximal order in G. So the orders in G mod K cannot be bigger than the orders in G. So that is going to be the order, and that is the maximal order also in the quotient. Okay, so here's the proof of my claim. Suppose that the order of GK is actually smaller than the order of G, which is P to the M. Then, well, I have, on one hand, I have K is gk to the p to the m minus 1th power, has to give me the order has to divide p to the m minus 1, so this power of gk has to be the identity in the quotient group, and this is g to the p to the m minus 1 k, and that tells me then that g to the p to the m minus 1 is in k, but it is in K and in the subgroup generated by G, which I knew K intersect the subgroup generated by G is identity because H itself was not in K. This is identity, and therefore G to the P minus 2 to the P to the M minus 1, that would be the identity, but then that is a contradiction. That is a contradiction because the order of G is P to the M, not to the M minus 1. And therefore, the order of GK is also P to the M, and thus GK is of maximal order P to the M, and also in the quotient G modulo K. Great. So now, what this tells me, the induction hypothesis tells me that there is a subgroup H, let me call it H tilde for now, in G modulo K, such that G modulo K is isomorphic to the element of maximal order, the subgroup generated by the element of maximal order, cross some subgroup H tilde. But the correspondence theorem, remember we proved the correspondence theorem for quotients. The correspondence theorem for quotients told me that subgroups of a quotient group actually come from subgroups of the group that contain K. So it tells me that there is some subgroup H in G with K containing H contain G, such that this H hat, a subgroup of G modulo K, is actually H modulo K contained in G modulo K. So what this tells me is that G modulo K is isomorphic to GK cross some HK. And what I claim now is that that's the H I want for G itself. So let's prove that. So now I know that G modulo K is isomorphic to GK cross some subgroup H. And what I want to prove is that actually G is isomorphic to G cross H, internal direct product. So for that, remember, to prove that, I need a couple things. First of all, I need that the elements of let's say, of one group and the other commute. So if I have this and I have some H prime in H, then G prime H prime has to commute with H prime G prime. And that is true, yes, because G is abelian. So there is nothing really to check here because G is abelian, so that's always going to happen. The next thing I need is to prove that the intersection of the two is just trivial, is the identity. So how do I check that? Well, suppose that I have something in the intersection of G and H. Then I do know this, so let's see what happens with the coset BK. Then BK is in the coset generated by GK, because B is in the subgroup generated by G, so BK will be in the subgroup generated by GK also. And it is also in the intersection with H over K, because B is also in H. But the intersection of the two, because this is an internal direct product, this also satisfies the conditions of internal direct product. So this one and that one have to be of trivial intersection. So there is only one coset in here, which is K. That tells me that BK is K, and therefore B is in K. And therefore, I can upgrade this intersection that is not just intersect with H, is intersect with K, which is a subgroup of H. So B is in G intersect K, but we chose K. Remember, K was generated by some element H, and we picked this K to be disjoint from the subgroup generated by G. So this was the identity, and therefore B is the identity. And therefore, this is true. So we've proved that. Great. The last condition to prove that something is an internal direct product, we need to check that G is indeed the product of the two. So like this, i.e., that there is always some power of G and some element of H. So for some T, some integer, and some H in H, that gives me all of G. Okay, so whenever I multiply powers of G times something in H, I do get all of G. Let A be some arbitrary element of G, and then consider that we do know that G modulo K is isomorphic to GK cross HK, right? So if I consider the coset AK, that has to be some power of GK, let's say to the T, times some coset, let's say HK. That means in particular that the element A, which is on this side, has to be some power of G times something in capital K, let's call it K1, times something in H, times something in K again. But K is contained in H, so all of this is in H. So this is some GT times some H prime with this in H. Therefore, this does belong to the powers of G times something in H. And therefore, A does belong to that product, and hence G itself is this product. And now we've satisfied all the conditions of an internal direct product, and so G is isomorphic to the subgroup generated by G direct product with H. This proves the induction hypothesis, and therefore by the lemma, that the lemma is true for all such G. Great. So now we can use that to prove what we want using induction again. So let's see how we do that. Theorem, let G be a finite Abelian P group for a fixed prime P. Then G is isomorphic to a direct product of P. There is just one P right now. E1 cross z modulo p to the e2 cross z modulo p to the e and z, where the size of G is p to the e1 plus e2 plus en, and we're going to order these in increasing order, and e1 is less or equal to e2 is less or equal to en. Okay, so let's prove this by induction. So we know that G is some power of P, and we're going to do induction on N. So if N is 1, then G is of order P, and G is isomorphic, it's cyclic, so it's isomorphic to Z modulo P, and the statement is true. Now, if we assume that the theorem is true, holds for every k up to n minus 1 by a strong induction, and now suppose that the size of G is p to the n, by the lemma, the subgroup G will be, and suppose that the element of maximal order is some element G of order p to the en, let's say, then by the lemma, G is isomorphic to some H cross the subgroup generated by this element Z, this element G, which is isomorphic to H cross Z modulo P to the en Z. Okay, and H is now of order less than the order of G, which was P to the n, and therefore this one is some p to the m with m strictly less than n. So by the induction hypothesis, H itself is isomorphic to the theorem holds here. So now this is going to be isomorphic to powers of P, cyclic groups that are of order powers of P up to Z modulo P to the n minus 1 Z, and hence G itself is isomorphic to H, it's isomorphic to H and the last piece, so it's isomorphic to Z modulo P to the E1 cross Z modulo P to the En minus 1 Z, which is the part that corresponds to H, cross the last piece we broke off like that. That's supposed to be an N right here. And therefore, that proves the theorem. So that proves the induction step. And hence, the theorem holds for all such G. Great. So what that tells me now is that the theorem, let's go back to the statement of the theorem. This tells me that the group, that the fundamental theorem of abelian groups holds for finite abelian P groups. And now I can put it all together to prove the big theorem, which is the fundamental theorem of finite abelian groups. And let me just do the proof. Let G be finite abelian. And then we know that step one is that we know that G is a direct product of P primary components. P1 cross GPN, or the P primary components. GPI is a P primary component, which is a P group. It's an abelian, finite abelian P group. So by the theorem that we just proved, each one of those is isomorphic to some copies of some direct product of cyclic groups, each one of, let's say, I1z up to z modulo pi to the I, and then some, let's say, niz. And therefore, what happens with G? Now I can put it all together. There will be, for the first prime, there will be E1, 1 up to z modulo P1, E1 to the N1, and then for the second prime, etc., up to the last prime, which would be the nth prime to the N, comma, and that would be a 1 here. Up to however many copies are there of the last one, up to and I guess not great notation, but it works. And that proves what we wanted, because now G is the direct product of cyclic copies of the direct product of cyclic groups, each one of a prime power order. Okay, so let's do one example. I just went through two examples, and then my computer crashed and I lost those pieces of the videos. So let me just go through the slides that I've already created. So let's talk about this group. G is z modulo 40, and I want to try to figure out what is the decomposition that the theorem gives me. The size of G is 40, which is 2 to the cube times 5. So I know there is going to be a 2 primary component and a 5 primary component, a non-trivial 2 primary component and 5 primary component. What elements have order a power of 2? For example, 5 has order a power of 2 because 5 times 8 is 40. So 5 has order 8. 10 has order 10 times 4 is 40. So again, we're talking about z modulo 40 additively. So 10 times 4 is 40. So 10 times 4 is 0. So 10 has order 4. And so on and so forth. 15 also has order 8. And you can see that actually all of these elements will have order a power of 2. The 2 primary component is a subgroup, and I know that every subgroup of z modulo 40 has to be cyclic, so it actually has to be that it is cyclic generated by 5. The cyclic group generated by 5 has 8 elements in it, and I know also that the order of the group, I know that the group has to be isomorphic to the product of the p primary components. So this p primary component has to have order 8. This has order 8, so that is the 2 primary component, is the subgroup generated by 5. Similarly, the subgroup generated by 8, 8 has order 5, because 8 times 5 is 40. The subgroup generated by 8 has order 5, so that will be the 5 primary component. So the theory tells me that G is direct product of the 2 and 5 primary components, and this is the 2 primary component, this is the 5 primary component. Now, this one is, you see, it is cyclic of order 8, so it's isomorphic to z modulo 8, and this one is cyclic of order 5, so it's isomorphic to z modulo 5. So therefore, z modulo 40 is isomorphic to z modulo 2 cubed times z modulo 5. And this is the decomposition that the fundamental theorem tells me. Now, what if we ask the sort of like the opposite question? We start from a group that is abelian of order 40, and I want to know all the possibilities. Again, I know that G will be the direct product of the primary components. The 5 primary component has to have order 5. Therefore, it is cyclic of order 5, because if you have prime order, you are cyclic of order 5. The 2 primary component has order 8, and now there is 3 possibilities. There is the one that we had before, but there is also Z modulo 2 cross Z modulo 4 and 3 copies of Z modulo 2. So that tells me that G, there's 3 possibilities, depending on where the 2 primary component is, up to isomorphism. It can be Z modulo 8 cross Z modulo 5. By the Chinese remainder theorem, this is the cyclic group for the 40. Then if you have Z modulo 2 cross Z modulo 4 for the 2 primary component, you can also express it as Z modulo 2 cross Z modulo 20. Or if you have 3 copies of Z modulo 2 in the 2 primary component, you can put these ones together and get Z modulo 2 cross Z modulo 2 cross Z modulo 10. So these are all the possibilities. So there's exactly 3 such abelian groups of order 40. Okay, so I think I'm done with this section, and then we're ready in the next video to talk about group actions.